Podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to do a little physics history. And we're going to focus on one guy in particular that was really helpful to Newton. So, in the beginning, in a sense, there was Aristotle. Very famous Greek scientist, thinker, teacher. He was wrong pretty much about everything he had to say about physics. He had all kinds of ideas that I'm not going to rehash here, but all of them were pretty much wrong.
Right.
Great biologist, lousy physicist. His ideas unfortunately stuck for a very, very long period of time. We just couldn't seem to shed them because we didn't have better explanations.
Well, and I think that part of the reason is because of the church, too. I mean, the church was pushing
They didn't help.
Right.
Then along comes this Polish priest named Nicholas Copernicus, who actually says that the Earth goes around the sun. And you just mentioned the church.
Yeah, that's not a popular view in the church.
It wasn't a popular view at the time. He waited to publish this until the day after his death. He had an assistant. He told his assistant, publish this after I die. You can put my name on it, because at that point in time, he knew he couldn't be persecuted for it. There was a guy by the name of Tycho Brahe, and he looked at Copernicus's work. He tried to do some math, and he took some observations. And there was a guy named Kepler, who we're going to focus on today. He inspired Galileo, whose name I can never spell right, and that's still not right. Galileo, who popularized the work of Copernicus, Brahe, and Kepler. There was a guy by the name of Edmund Halley, Halley's Comet.
Right.
That was a contemporary of Newton. Newton is quoted as saying something about, I'm only here by standing on the shoulders of giants. He could not have done what he did if Copernicus hadn't swatted down Aristotle, and Brahe and Kepler hadn't done some of their work, and Galileo hadn't popularized the idea, and Halley collected data about the comet that's named after him. Newton took all that work and he put it together into the universal law of gravitation, the three laws. He invented calculus. He did all these other things. We want to focus on Kepler and specifically his three laws. We're going to have you do the questions, by the way, on pages 388 and 389. But Kepler's first law, he had three. First law was that, contrary to what Copernicus said, planets, comets, moons, they travel in ellipses.
Not in circles.
Not in circles. This was huge. Now, some of these ellipses are very close to circles.
Right.
But that means that there are two foci, and that led to some of his other work. His second law is called equal areas in equal time.
Even to me, this is sort of interesting if you think about it, that these ellipses, the planet going around sweeps out an equal area in equal time.
So if this is one of the foci, and this takes 2 months. I'm just picking out a number here. All right. Then the same area must be swept out on the other side of this. So the area here and the areas here have to be the same, and it takes the same amount of time. And that that nature follows these very keen geometric proofs, which is really quite remarkable. And this is a very complicated proof, and one that maybe you can get a geometry teacher to do for you, but I'm not going to be doing that. And then the other thing, the icing on the cake, was that if you took the period and you squared it, and you divided it by one of these distances to the foci, and you cubed it, this would be a constant. And when he does this, it all ties together. First of all, equal areas and equal time is not possible unless you're talking about ellipses. This t squared over r cubed is a constant, is not possible unless you start talking about ellipses and not circles. So Kepler took these observations And the circle idea that Copernicus introduced was a carryover from Aristotle. Aristotle said, hey, look, the sun goes around the earth and there are circles. But it was Kepler that really swatted Aristotle completely out of the way and said, no, in order to explain this, we have to be talking about ellipses. The reason why is if this is the sun, and we do talk about perfect circles, you can make observations for years and the circle holds up. But then all of a sudden, the seasons aren't starting when they're supposed to happen, and the calendar's out of date, and there's all kinds of things. So they came up with this explanation, oh, but if they travel in tiny circles within circles, well, then the explanation holds up. And that worked for hundreds of years. Fantastic. And then things got out of whack again. And then they started doing, well, if we go tiny circles within larger circles, within the big circle, then it all works out.
Right.
And at some point, I'm sure I'm going to spell this wrong too, it's called Occam's razor.
Right.
Occam's razor says if the explanation becomes too complex, it's probably wrong.
Right. The simplest answer is usually correct.
Is usually the right answer. And Kepler applied Occam's razor and said, this is silly, let's try this.
You can solve it with this.
And he solved it with this, and Galileo popularized this and explained why the people that believed in the sun going around the earth and perfect circle concept were wrong. And as a result, we had Newton, and the scientific revolution was able to take place as a result of this. So you guys are responsible for wrapping this up and doing those questions.
I think the questions are pretty easy. It talks about the acceleration due to gravity on the moon and things like that.
Sure. So I think they can handle that.
Yeah.
So signing off, this is Mr. White.
And Mr. Sadler.